All right, so we're looking now at free-falling objects. Free-falling object means that I have an object that's just falling within the Earth's gravitational field, so it's falling under the influence of Earth's gravity. That means that it's going to have an acceleration equal to a value that we call g. Now, this acceleration is downwards, and so it's negative, and that's where this negative sign comes from. Now, when we refer to g, g has a constant for the planet Earth. It's equal to 9.8 meters per second squared. So on the planet Earth, we would say that A is equal to negative 9.8 meters per second squared. The negative, of course, showing that it's in the downward direction. Now, so that's our acceleration, and otherwise they're just basic kinematics problems. Let's look at a problem. This is from a video of the redbull stratos. So you can watch this. I have a little excerpt from it. The redbull stratos. Remember, this was this guy that went up in this balloon and jumped out of this little capsule. You can go ahead and click on that video. You're going to watch from 3:30 to 4 minutes. When you start seeing the velocities kick up on the video, you can stop watching there. He really just falls to the ground. If you want to watch the rest, that's fine too. So you can go ahead and click right about here and watch that video. All right, so on the video, at t equal 21 seconds, we find that his velocity or his speed is downward at negative 697 kilometers per hour. Now I want to convert that into meters per second, so let's go ahead and do that here. 697 kilometers per hour. In 1 hour, there are 3,600 seconds, and in 1 kilometer, there are 1,000 meters. So 697 kilometers per hour is the same as 194 meters per second. So this is what his altimeter or whatever gives as his speed. So we have a time and we have a speed, but we also know his acceleration because he's falling within the gravitational field of the Earth. It's negative 9.8 meters per second squared. So let's just do a check on this and see. I'm going to use my kinematics equation. That is V is equal to V naught plus A times T. My V naught, this is my initial velocity. This was his velocity, just before he jumped. And it's equal to 0, so it's going to have 0 minus 9.8, or rather plus a negative 9.8 meters per second squared, times T, which was 21 seconds. And 9.8 times 21, I get 206 meters per second. It's pretty close to 194. Now, the difference here is likely that there could be several things, but actually one of the things is there is some amount of air resistance. And so this value, which is the actual measured value, is a little bit lower than what you might expect without any air resistance at all. So with a little bit of air resistance, it can actually slow them down a little bit. There are some other things too, but we won't get into that. We also want to know what distance does he fall in that time. So we can use our other kinematics equation. Y is equal to V naught T plus 1/2 A T squared. So that gives me V naught again is 0. If I want to know Y, it's just equal to 1/2 times negative 9.8 meters per second squared times T, which was 21 seconds, squared. So he's fallen about a half a mile, 2,200 meters. Excuse me, no, more than a mile, about a mile and a half. So 2,200 meters in 21 seconds. Again, that's about 1.5 miles or so. All right, so those are basic free fall problems. They're really just kinematics problems, except anytime you find something that's falling on the planet Earth, we'll always know its acceleration to be negative 9.8.